Okay, so we looked at how to delete from a binary search tree yesterday, on Monday, whenever it was, right? We went through those three cases that if you are removing as a leaf, right, it's pretty straightforward. All you have to do is sever the parent's reference to it, right? If you are deleting, say, something that only has one child, though, right, what do? Well, you just circumvent it just like a linked list. And remember that we have both children and parent references. So it's like a doubly linked list where you're going to have to circumvent it down and you're going to have to circumvent it up. Okay, so the parent here is going to have to be set as well. And then we discussed the third case where, right, we discussed the third case where if I've got, what if I want to delete 50? Let me ask you, how do I delete 50? What, did we talk about this? You did? Okay. So what do? You look at the left subtree, or you could look at the right subtree. But let's look at the left subtree here. What among these things could I promote up to this new this root so that it's still a binary search tree? 49. Why 49? Because it is the max element. Right? I put 49 up here, and then I can delete 49. Right? Do I get into trouble if there are two children there? No, that's not possible, because then it would not be the max. This would be the max instead. So there's guaranteed not to be a right child on this. And we know how to deal with that. We simply just circumvent like we did with the second case. Okay? So now let's come over here to our binary search tree implementation, and let's go ahead and implement this remove method here. There's something problem up here. Oh, I already had it up here. Oops. All right, there we go. I changed this to a Boolean because what we're going to do is we're going to communicate back to the calling function whether or not it had an effect. Because the first step here is going to be what? 1 or 0 in fact. Find the element, or find the node containing x, dot, dot, dot. If no such node, then return false and do nothing. It's a noop, no operation. Okay? So removes the given element x, oops, code x, from this tree if it exists, and returns true. If no such element exists, returns false. Code false. There we go. All right. So that's where we're going here. So find the node containing x. That sounds real familiar to me. Right? Contains. Now be careful here. Contains was a Boolean. Is that going to give us the node? No. Let's redesign it. Refactor it. All right. Let's go ahead and create another function here. Initially public. Binary tree node t get node containing the element x. And it's going to be pretty much a cut and paste of this method right here, except that instead of returning true and false, what am I going to end up returning? You find what you're looking for. True, it exists. I'm going to return the current node. Otherwise, I didn't find what I was looking for. What is a flag value to indicate that it doesn't exist? Null. Binary tree node. There we go. And fix that up. There we go. Repeated code, repeated code. Should I be doing that? DRY, don't repeat yourself. Let's go ahead and refactor this one. This one is a little bit more general, right? It not only tells you that it's there, but it gives it to you if it is. This one's a little bit more specific. All we need to do is call that other function, this dot get node of x, right? And determine if it's null or not. Right? U equals, there we go. If u is not equal to null, then that means that you found it. Return true. Yes, it contains that element. Otherwise, return false. There we go. All right. 2 improvements. First of all, can I improve this if-else-if statement here? If this expression is true, then return true. If that expression is false, then return false. What should I be doing instead? return the expression. Right? Much simpler code. Okay. The second improvement here. Should I be allowing the outside world access to the internal representation of this binary search tree by giving it binary search tree nodes? Probably not. That's a leaky abstraction. I'm leaking information to the outside world. So, private. Right? That's perfectly fine to have this method here that breaks encapsulation. As long as you make it private, you're not breaking encapsulation. Right? For example, in your sorted list that you're doing this week, if you have a remove, add at index, right? That's perfectly fine as long as it is private, right? Because that doesn't allow the outside world to arbitrarily insert elements wherever they want, right? But it might still be useful to you if you want to use it. Right? And by the way, the hint that I'll give you on the sorted list ADT, we've given you we've given you 95% of the code. You just need to tweak it a little bit, okay? All right, so contains, get node, in order, et cetera, et cetera. So find the node, right? I'm going to cut and paste this code right here. Contains. Find the node containing X. If no such node, in other words, if U is null, then I will immediately return false. No operation. Otherwise, if I get past that, then I know that I've got a valid node that I now need to take care of. Let's take care of that first case where we're deleting leaves. Come on. Right. So for example, 12 here. Right. By the way, I'm already taking care of the instance in which it doesn't exist. 13. 13 does not exist. How can you delete it? I've taken care of that. Right. What about 12 here? It's a leaf. So if my node is a leaf, if U is a leaf, ... Right. Then what do I need to do? I need to make U's parent point to null, right? And make U's parent point to null, make U's parent null. I'll say it like that. Right? It's kind of weird saying it, right? All right, there's my pseudocode. How do I know if U is a leaf or not? It's kind of a question for whom? Hey, U, are you a leaf? Who am I asking there? I'm asking you. What is U? It's a binary tree node. Who should be answering this question then? The binary tree node class. Good encapsulation. I want to know if you're a leaf. Public Boolean is leaf. How do I know if you're now I'm me. Now I'm this. How do I know if I'm a leaf? If I have no left child and I have no right child, right? So if return this dot left child is not equal to null, and this dot right child is equal to null. Right? If my left child does not exist and my right child does not exist, then I am a leaf. Right? I'm a leaf on the wind. Right? Anybody watch Firefly? No? Okay, fine. Don't have any common interest at all here. If is leaf. There we go. All right, there we go. If you're a leaf, then I need to make my parent point to null. Okay? U dot get parent dot left or right child. Left or right child dot like set left or right child to null. There we go. That's what I'm doing right here. I'm making U's parent, I'm getting the parent, and then I'm setting either its left child or its right child to null. Let's take a look at my diagram here. In the case that I am deleting 12, I would go to the parent and I would say, no, your left child needs to be null. But what if I'm deleting 28? I need to go to the parent and say, oh, you need to delete your right child instead. How do I know the difference from the perspective of the thing that I'm deleting? Square is good enough. I need to know me. Like, am I a left child? In which case I tell my parent, set your left child to null, because to delete me. If I'm a right child, I say, parent, set your right child to null to delete me. So let's spread that out as two pieces of pseudocode here. If u is a left child, then u.getParent.set left child to null. Right? Else if, you know what, let me write it like this. If u is a left child, then do this. There we go. Else, if u dot is a right child, then u dot get parent dot set right child to null. There. And then make use parent null, u dot set parent to null. Just to get rid of that that reference right there. Okay? Once again, I have a question here. Hey you, are you a left child? Hey you, are you a right child? Who should be answering that question? The binary tree node. Remember that we have this has left child, has right child? Right. Boolean is left child, right? And Boolean is right child. Is right child. How do I know if I'm a left child or not? This is where that poem, that brain teaser poem comes in. Brothers and sisters, I have none, but this man's father, my parent, is my father's son. Who am I? So brothers and sisters, I have none. I'm a left child. Am I a left child or not? This dot get parent, right, dot get left child. Is that me? How do I say me in object-oriented programming? This. If this is equal to my parent's left child, then I'm a left child. Right? And I return that. Now, otherwise I return false. So I'm going to return this expression right here. Now be careful. Can I get the parent? Maybe. Maybe not. Is there a node here that doesn't have a parent? The root. Right? So let's make sure that I'm not the root. Right? So, I don't know. Am I a left child? Is this good enough? Yeah, because you're asking whether or not the, so if this dot parent is not equal to null, and this dot get parent dot get left child is equal to this. That should be good. Right? I do, oh, and. Was that? Well, in isolation, yes, I do need it here, right? Because is the root a left child? No. Is it a right child? No. Right? Everything else is either a left child or a right child, but it's that one thing, the root, that is neither. And so I do need that, because what if I've got a tree, a binary search tree that's just 50, and I still want to delete 50, right? And I'm asking those questions need to have the correct answer. All right, same thing here, except for get the right child. Is that me? Right. And now I can go ahead and answer those questions in plain old code here. If u dot is left child, there we go. U dot is right child, there we go. All right. Okay. Now think about that corner case here. What if I only have one element in the tree? It's a seed, that it looks like this, 50. Right. And I want to delete 50. Right. I probably need to take care of that as a corner case, right? So to do, take care of the case where the tree has one node, ... I'll do that. I'll leave that as an exercise. Okay. But otherwise, if I take care of that separately, then I'm making sure that that's taken care of, and hopefully that addresses the issue. Right. All right. Else if. something. Right? What if I'm an only child and a left child? Right? What should that look like? Else if I'm an only child, and a right child. Right? I'm a right child and I'm the only child. Versus else both children are present. Right? Sorry, it's not an only child. Only child would be a leaf. Duh. No, I am an only child because I have a parent, and I'm a left child. Right? Versus I'm an only child and I'm a right child. Versus the both children are here. I'm not an only child. Right? Both children are present. Okay, we'll take care of that later here. So help me out. Only child and I'm a left child. How do I do that? Let's diagram it. What does it look like? Here is the current node U that I'm deleting. It potentially has a parent, right? And I'm the left child of that parent. I potentially have both children or not children? Nope. I only have a left child. That's what, oops, sorry. That is the situation that we have here. So what do I need to do to circumvent this, and what do I need to do to circumvent that? No? So, well, first of all, how do I answer the question here? Right. U dot has a left child, and U dot has right child is false. It has a left child, right? But it doesn't have a right child. Okay? Let's take care of that. U dot get parent dot set left or right. All right, oops. Set the left or right child to use left child. Right? Because it has a left child, but it doesn't have a right child. So which one gets set? Let's take a look at our diagram again. Right? 15, let's see, here. 24 is a right child, 49 is a right child. Right? You would set the right child here, but would you set it to use right child or it's use left child? Oh, sorry. What do I want to look at here? 45 and 24. Now I'm confusing myself. Let's just do 45 here. So I have a right child, but I have no left child. Which one is that? U dot has left child is false, and U dot has right child is true. There we go. So that's deleting a 45, right? Deleting 45, dot, dot, dot. Right. How do I do that? U dot get parent. I need to set its left or right child. Set left child to U dot right child. Or do I do right child to the right child? Which one is it? I need to check. What do I need to check? It's, oh, well, I need to check my parent, am I a right child or not? If U dot is a left child, then I do this. Otherwise, if U dot is right child, then I do this. I haven't been testing this along the way, but is this correct? Make sense? Right. Left, right, BA start. I think that this is right. Right. So now what should this look like over here? It's going to be the same thing, except that, what do I change? U has now a left child, not a right child. There we go. Could you simplify this? Yeah, probably. Write out a whole logic grid and then get it down to maybe 2 lines of code instead. Right? Because I have this condition right here and this condition right here, and this condition, right? I could collapse those all into one big giant if-else if statement. But I like this because I'll simplify it and refactor it later. Right? I'm just enumerating every single possibility here. Okay. Before we go on, let's go ahead and test this. And to do that, we're going to have to make sure that this actually compiles and return true. True. There we go. Now, we're not going to be able to test this case here because there's no operation yet. We'll come back to that. Okay. I've got my binary search tree over here, my large binary search tree from my demo class, tree utils.large BST. There we go. And did we talk about Tixie? Yeah, we talked about Tixie. Good. Here it is. There we go. We're going to print it out, and then we're going to test a bunch of things. Let's come back over here to our diagram. Let's go ahead and delete 1, 2, 3, 4 leaves. And let's make sure that those all work. Once I've done that, let's go ahead and delete 1, 2, 3 internal nodes. Let's do 15 instead. So 1, 2, 3, 4, 5, 6, 7. All right. Let's delete them in that order and see what the results are. Okay. So t.remove 2, and then print it to Tixie. Let's remove 12. Right. Let's remove 75. 48, 75 is what I said. 48, 75. There we go. Those are all my leaves. Oops. My internal nodes would then be 15, oh no, sorry, 24 and 45. 24 and 45. There we go. Run it. It actually ran, it terminated, and it printed all of these out. So let me come over here and cut and paste them. And now we're going to have a whole bunch of diagrams here. Here's the original diagram on the left. Remember that we deleted 2 first. 2 was a leaf. Did it work? Yep. Then we deleted 12. 12 is also a leaf. Did it work? Yep. Then we deleted 48. I think I said 48, right? Where's 48? 48 is another leaf. Did it work? Yep. Then we deleted 24. 24 right here, so 28 should come up to that. Uh-oh. Oh, 75 first, was it? Oh, yeah, it worked then. All right. Then 28. And that worked too. All right, see, 28, or sorry, 24 is what we deleted, and then 28 came up to be the new child there. And then the last one that we're going to delete is 45 right here. 49 comes up to be that new child there. I'm somewhat convinced that it works, but do be careful. Did we ever take care of the parent? Like the parent reference of u. U dot set parent to null. Okay? And u dot set parent to null. That's not going to show up in that diagram because we're only going top to bottom. But if you ever went bottom to top, then it would be screwed up if you didn't take care of the parent references as well. All right. Oof. Both children are present. Let's outline this on my diagram first. Okay. Let's go ahead and do it with 50. All right. My first step is, of course, to find it. Find it. And we've already done that. So 2. What I'm going to do is I'm going to go to the left subtree. That means that I'm going to establish some current variable here that starts out at the left child of whatever we're trying to delete. Right? We're trying to delete this. Okay. 3. How do I find the maximum in the subtree here? Just keep going right until you can go no further. There's the max right there. Go right until the end. Okay? Then 4, replace. u with max's element. In other words, what I'm going to do is I'm going to go ahead and erase this 50 right here. There we go. And I'm going to replace it with 49. Right. We still have to take care of this 49 right here. Right. So 5, delete the max node. Okay? Pretty straightforward. Found it, we're already did that. So let's establish a new variable here, which is going to be a binary, I'll outline this here. 2, go to the left. Right? And so binary tree node t, and I'll call this current, and I will say u dot get left child. Right? I'm going to go to the left. Then 3, find the max. Go to the right until you can't anymore. Dot, dot, dot. Help me out with that. What kind of a loop do you want here? For loop? While loop. While the current is not equal to null, that means that you'll fall off the tree at some point. So when do you stop? While the current has a right child. See how convenient those things are? Right? While the current still has a right child, then go right. Current is equal to current dot get right child. Right. Cool. Let me move this back up there. Right. Step 4, replace the u's element with current, which is the max's element. I'm only half regretting that I didn't call this max. Right? You could go back and call this max. I didn't regret it too much because at first it's not necessarily the max. It's the current. At this point, at this point, current is max. Dot, dot, dot. I will put that into my notes here though. Right. So replace u's element with current's element. So u dot set element to max dot get element. Oh, not max, but current, sorry. Current dot get element. That's not going to work though. Do you remember the design of our node? Let's take a look at it. Is there a setter for element? No, because it is final. But now I have a very good reason, in other words, a VGR, in order to make it not final, so that I can do something like this and have a setter. Void set element. This dot element is equal to element. And then we need to take that element, t element. There we go. Good? We just redesigned it a little bit. Once we had a very good reason to redesign it. Okay? Now 5. Delete the current node. Dot, dot, dot. We know that it has at most one child, right? The current node could be an only child, right? It has no children at all, right? It could be that it has one child, but it can't be the case that it has 2 children. So we know how to deal with that. Take this, this, and this, and cut and paste it on all, and put it right here, and replace everything with current instead of u. That doesn't sound right to me. Let's redesign this function before we think about doing that. Okay? Actually, let me do this. I'm going to go ahead and get the node, and I'm going to end it right here. And I'm going to delete the node u. Dot, 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 and I should just put these in comments. Delete the node u. Dot, dot, dot. And then finally return true. Now I don't want to lose all that code that I just wrote, but I'll rename it. I'll make sure that it's private so that you can't screw up my tree arbitrarily. Void, delete node, tree, binary tree node, t, and I'll call it u because that's what I call it in the function there. So if I had that method, I could go ahead and just call that method. Delete node u. Nice. Now why does that help me? I need to delete the current node. So delete the node that you want to. Clever. Why is that clever? It's a little bit of recursion, just a little bit of recursion. Now, are we at risk here for a runaway recursion, where delete, 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 and I don't want that to happen? Think about how you got here to begin with. You have both children, right? So you go and you find the maximum, which only has one child, at most one child. So when you go and to delete the max or the current right here, is this ever going to happen again where you would end up calling the recursion yet again? Nope. Because of the design and because of the reasoning that we had over here. That the maximum is not going to have a right child. Okay. Fix it all up. Good. That looks good. I do need to take care of the parent though. Before I leave. So u.set parent to null. There we go. Let's come over here. We didn't break anything, but how could I rigorously test this without having to cut, paste, cut, paste, cut, paste? I want to test all of them. I'm going to go over here to the large BST to see how it was built. I took this string of elements, treated them all as integers, and then added them all. Let's repeat that over here in reverse. T.remove x. And I'm going to remove them in that order, 50, 40, 60, 20, 45, dot, dot, dot. And each time I'm going to print out the result. System.out.println tree utils.toTixie. Darn, what was it? T? There we go. There. All right. This nice little tool that I built that visualizes it by simply just dumping a bunch of Tixie code, right, will now show me all of those steps. Right. Might take a little bit to compile here because now I do have like, I don't know, 20 diagrams. Once it's done though, there we go, all the way to the beginning here. There's the original tree. We're going to delete 50 first. Remember what happens? 49 comes up and then 48 becomes the new child of 45. Good. Now I'm going to delete 40 here. So it has two children, so what would you expect? Go over here, get 28, which is a leaf, and so it gets deleted, and 28 is now the new 40. Looks good. I'm going to delete 60 now. Well, it only has one child, so that 90 gets promoted up. Right? Dot, 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 you could verify as you go along. Right? At the very end, what should you expect? Uh-oh. Come on. What? 12 all the way. Maybe it's maybe I reached its limit. I don't know. That's weird. It was able to picture all of them in the last class here. Just have to kick it in the butt, maybe? Nope, I don't know why it's not working. Oh well. It could, well, okay, it's repeated, repeated, repeated. Ooh, yeah, we've got a bug here. Darn it. Let's find out where it stops working. So it works on 95. Then what would we do next? 2. Uh-oh. 2 did not get deleted. When do we delete 2? Right there. Okay. Does anybody see the error or bug? Otherwise, I'll just post the correct code later on. Right. It's somewhere in there. It happens when, let's see, 2 is, there's one child and it has a right child, and it is a left child. So, has a right child, it would be this. Let's get rid of this. And it is not a right child, but it was 12, or 2. It is a left child, and it has a right child. Is left child, u.getParent set left child to my right child, which should work. 12 should come up. Oh well. I'm not sure. Maybe it's just the visualization that's wrong. Yeah, do you see it?
No, I just have 248.
248?
Yeah.
Oh, wait, say again?
248.
Oh, there were 248s? 48 and 48. Oh, good point. So let's go back. Let's rewind. When do we get the duplicate 48 there? 48, 48, 48, 48. Still only 148. 48. There we go. All right, so it happened from here to here. No, from here to here. When we end up doing 49, there we go. We set the parent though. Maybe we don't set the parent somewhere else? I'm not sure. Anyway, I've got a working version somewhere. In fact, your lab has a working version. We did the delete method already for you, I think. Right? Did we? All right. All right, any questions on this so far? Otherwise, this is a different way of testing. In your lab, the way of testing is, of course, we built all this into a JUnit tests. Right? In fact, we might have used this tree. I'm not sure. Anyway, let's go ahead and get rid of all this and come back over here. Now, remember that binary search trees can be degenerate. They can be skewed. We call those linked lists. Right? There we go. ... 100. We could have it so that the depth, which is D, is order n, in which case we're right back to square one. Now, like I previewed, if you do have a case where it's skewed to the right, you can do these rotations to reorient them. So you can have 10, then 20, then 30. Or you could have a left rotation or a left-right rotation or right rotation. Those are all AVL trees. And there are a couple of other dozen rebalancing binary search trees that work that way. I want to look at a different type of tree called a heap that is guaranteed to have logarithmic depth, but at a cost. Stacks and queues were efficient because we restricted the access to only one location. Right? Here's a stack, very organized. You can go ahead and put stuff in, but you can only put it in one area. Right? Now, remember back to CS1, that the program stack, that's your memory where it's a call stack. What's the other location of memory? The heap. This is where you call malloc in C to allocate memory on the heap. The heap is more of a pile, right? It's less organized. It's more, but it's larger. Right? So now imagine a heap like a garbage, or I usually say laundry or something like that. Where do you throw something onto the heap? It's less organized. So can you put something? Oh, I want it right there. What usually happens if it's disorganized? It might fall a little bit, right? And it'll end up right here just due to gravity. You usually throw them on the top, and then they trickle down here. Sometimes they trickle into the middle or whatever. But that's what I see when I see a heap. Now, if you take something off of the bottom of the heap, what's going to happen? It's going to collapse, right? So we're only going to work off of the top here. Right? We're going to have two basic operations for our heap. We're going to have add element. I'll rephrase that. Add element. Not at an arbitrary location. It's going to just be put into the heap. Where it ends up, who knows? It could trickle all the way down. It could trickle into the middle. It could stay up here. Right? Something like that. The other operation we're going to have is get min or max. Because the heap property is that the minimum or the maximum is always going to be at the top of the heap. Okay? So that's what a heap is. Definition. A heap, a min heap, is a binary tree. It's not a binary search tree because that would be the binary search tree property, but it is a binary tree such that 1, the key at any node is less than both its children. Now, does that sound like a binary search tree to you? No, it's left child, everything is over here is less than it, everything over here is greater than it. So what I'm saying is that the key, here's my key, this is less than k, or sorry, no, this is min heap, so scratch that. Greater is what I wanted to say. No, this is correct. Why am I I'm confusing myself. It's less than both of its children, so its children are greater. There we go. There we go. All right. It's not a binary search tree. It's greater than on both sides. What do we do about equality? We don't worry about it. We just make sure that everything is unique. Right? And 2, I'll move this over here so we've got that visualization. It is full. This is the fullness property. Full. So it's shaped like this, where every node is at every level except for possibly the last level. The last level could be full, not full, but it's going to be full to the left, right? So it's still full to the left. Right. Let's take a look at a concrete example here. I'm pretty sure I have an example. Min heap, there we go. All right. Now, this is a min heap. You can verify it. We'll verify it here in a second. But is this a min heap? If I were to get rid of something like this. There we go. Is that a min heap? It's not full. This part is missing now. But you can observe that this heap right here is full. Every node at every level is present except for the last level, but it's full to the left. Right? If I were to add a node, say right here, right there we go. Come on, black. Right there, and not a node right here, then it would no longer be full. Okay. If I were to have a gap right here, right, it would no longer be full. So the fullness property guarantees that everything is full up until the last level, and it's all full to the left. Okay. That guarantees that D is going to be order log n. Right. Is that apparent? Right, because that goes back to why do we look at trees to begin with? Well, if we've got a full tree, then the number of nodes is n. The depth will be logarithmic with respect to n. Right. How many nodes do I have here, by the way? Let's review that. 1, 2, 4, 8, and then plus 2. At the end. Right? It follows this, what is this progression right here? It's a exponential, we call that a geometric progression, right? I thought so. Anyway, it's full. Now look at the values stored in here. 1 is greater than both of its children. Now, its right child is greater than its left child, just like a binary search tree. Does that sound like a binary search tree? No. But take any node here, and it's going to be greater or less than both of its children. What does that tell you about where the minimum is? It is always at the ... where? Top. Now, where's the maximum going to be? What's the maximum here, by the way? I think it's 95, right? Is there any rhyme or reason to that? I mean, it's certainly going to be down at the lowest level or the second to lowest level, right? How do you know, right? How are you going to go about finding the maximum? A BFS? A pre-order traversal? An in-order traversal, right? You'd basically have to search the entire bottom row of this heap to find the maximum. which is going to be order n no matter what. That's not its purpose. This is not a general purpose data structure where you can do basic CRUD. Put stuff in, take stuff out, retrieve stuff. This is going to be a restricted access data structure that only allows these two efficient operations. Put stuff in, get a very special value out. Let's visualize this. We'll understand how it gets fixed later on, but start taking things out. What if I called get min? What's the first thing that's going to be pulled out here? 1. Right? And then it reorients itself. We'll talk about that on Friday. What's the next thing that gets pulled out? Is it 5? Yep, 5. What's the next thing that gets pulled out? 30. Next, 40. I'm guaranteeing that the min is always at the top here, and that's what I pull out. So ... What's the last thing that's going to get pulled out? 95. Tell me about this sequence right here. It is in order. It's sorted. That's the algorithm that you're going to implement in today's lab at the end. I don't think that you have to implement your own heap. You use Java's heap, priority queue, right? And that priority queue is actually not a tree-based implementation. It's an array-based implementation. We'll talk about both of those, or at least the easier one, the array-based implementation. But you can imagine what a sorting algorithm would look like, right? For each x, insert x into a min heap. Right? Done. Now you take stuff, you put stuff in. Now you take stuff out. While the heap is not empty, x will be remove min and add x to result. Output result. What have I just done here? This is something called heap sort. And it's really dumb code. Dumb code as in it's not very clever code. It's straightforward code. You put stuff into a data structure. You take stuff out of a data structure. And magically, it's all sorted. This goes back to the very beginning of this course. Eric S. Raymond. Smart data structures and dumb code are a lot better than the other way around. This is dumb code, right? Put stuff in, take stuff out. Smart data structure. What would the other way around look like? Clever code, no data structure. We called that quicksort, right? So which one is better? That complicated quicksort algorithm that has recursion and this partitioning and it's very, very clever, very complex code. No data structures at all, just an array, versus this. Right? I like this a hell of a lot better. Right? Put stuff in, take stuff out. Put stuff in, take stuff out. Right? We have to be careful, though. Does it come at a cost? Is this still efficient or not? Does it beat quicksort, or does quicksort still, it's quicker? Right? Turns out that they're the same, right? But we'll have that full analysis by the end of the course. We need to first understand how a heap gets implemented and how we end up supporting these two methods here of add an element and then get the minimum element. Get and remove the minimum element. Okay? All right, we'll do that on Friday. That's not necessary for your lab today.